We have the third case, which is a is smaller than 0. A is smaller than 0 at that time. This one we have s squared equals a, and now here we have a is smaller than 0. A is smaller than 0, which means that a is square root of ai, and also plus or minus square root of ai, because this is a negative value. It should be it should be something like plus or minus square root of minus ai, because a is negative, so minus a is a positive value. So this is a positive value, we can take the square root, but we have square root of minus 1, so this is I here. Or we can just make, if a is a negative number, we can just make it to be minus k squared, so this is a negative value. So this is minus k squared, so we will have s equals plus or minus ki. In this case, we have ex to be exponential to ikx, and also e to the exponential minus ikx, something like this. Likewise, for this one, we have s squared equals ac squared. Now a is also negative, so we make it minus k squared c squared. We just change a to be minus k squared because a is negative. So s squared is this, so we have s to be plus or minus kci, because this is a negative. So we take the square root, will be k times c times I, like this. Yeah, so also we know that omega equals kc. Omega equals kc. Why it will be like that? Because in the textbook, we know that k is divided as 2 pi over lambda. If you still remember, we just talked about it yesterday. So we have k equals 2 pi over lambda. And we also know that c equals f lambda. So in this case, we can just multiply 2 pi here and then divide 2 pi here. So everything doesn't change. So 2 pi f is omega. 2 pi f is omega. And lambda over 2 pi, this is 2 pi over lambda. So this is 1 over k. So this is over k. So c equals omega over k. C equals omega over k, which means that omega equals kc. So we have omega equals kc. Here we have kci, which means that s equals plus or minus omega I, or I omega. So here we have s equals I omega t, so we have et equals exponential to I omega t, or et equals e to the minus I omega t, because we have these complex conjugate roots. So we have, this is ex, this is et, or generally we can write it as the combination of these two terms and the combination of these two terms, something like this. And then of course we know ext is the multiplication of ex and et. So let's say we have ext equals ex times et. Now we know ex will be just a combination of maybe just call it a1 exponential to ikx plus b1 exponential to minus ikx, and et to be c1 exponential to I omega t plus d1 exponential to minus I omega t, because we have ex to be this one, et to be this one and this one. So we can just write it as the linear combination of them. And we can just put this one here and put this one here. So we have ex of t equals a1 exponential to exponential I k x plus a b1 exponential to minus I k x. And then c1 exponential to I omega t plus a d1 exponential to minus I omega t. Okay, so we can just multiply it out. We have this term multiplied to be a1 c1 exponential to I kx plus omega t. And then we have totally all the four terms, but with the constant to be like this. So we can just rewrite it into a, b, c, d. So we have 1, 2, 3, 4 terms here. You can just multiply this one and this one. It will be this term because we have plus I kx plus I omega t. So we have two plus term here. And if we have two negative terms, minus I kx minus I omega t, we have minus I kx minus I omega t here, which is referred to this term. And if we have plus I kx minus I omega t, this is this term. And if we have minus I kx and plus I omega t, which is this term, minus I kx, and then distribute into it, it will be plus I omega t. Okay, so we have these four terms, and actually, the physical meaning of this four term is that this one refers to the wave propagate in x direction. This one refers to the wave propagate in the negative x direction. It's somehow like we have a minus sign inside, so refer to the positive x direction, which feels like if t is larger, x should be larger to remain the phase. Because you can simply imagine like if it is like exponential to I kx minus omega t, something like this. And if you still remember the Euler's equation, it is like a cosine kx minus omega t plus I sine kx minus omega t. Of course, it is complex, but yeah, just forget this at this moment. Yeah, so you can see it here. You can just regard it as phi equals kx minus omega t. In order to remain phi to be a constant, if t becomes larger, then kx should also become larger, which feels like that, yeah, when t increase, x also increase, so that the phi become still remains, which feels like when the time pass, the x-axis coordinate become larger. So it feels like the wave is moving in the positive x direction. And likewise for this one, we only have this term here, but in order to, yeah, if you still remember, if we have a negative sign, if we have a negative sign here, we only have a negative sign here. So yeah, so these two terms also refer to the wave propagate in positive x direction. If the term is like this, so you can feel like if the phase is constant, then if t is larger, then x should be smaller, so that the whole term will be constant. In this sense, t becomes larger, x becomes smaller. It feels like the wave is propagating in the negative x direction, and so as this term. So generally, the solution will be like this. Some of the waves are propagating in positive x direction. Some of the waves are a part of the wave are propagating in negative x directions. But for simplicity, it just tells you that we can just cope with one of the direction, and then yeah, it turns out to be just add them together in two directions. So in the textbook, it assumes that only the wave is only propagating in one direction, which is the positive x direction. So it only chooses the term like this, cosine kx omega t. Of course, in the textbook it uses sine, but yet it doesn't really matter because you can just change the phase to plus 90 degrees, then it is a sine function. It doesn't really matter. So this is actually the solution for the wave equation. But of course, we only solve the E field, and for the B field, we still need the Maxwell equation. Suppose we have this. Suppose we have the solution for the E field, and then we plug it back into the. This one is Faraday's law. This one is Faraday's law. So this one is Faraday's law. When we write it in one dimension, this curl is nothing but partial E partial x, partial E partial x, and then partial E partial x equals to partial B partial t. So we can just plug this one into here, or we can rewrite this one into partial B partial t equals minus partial E partial x, like this. We just multiply -1 on both sides. So here we take the partial derivative with respect to x, so that this one cosine, take the partial derivative, will be minus sign. So we have minus sign, and then here we also have a minus sign here, so it becomes positive. So we have positive sign of this term, and then also we have EM. And then for the chain rule with this, we take the partial derivative with respect to x, so that we only have k here. This is just a constant term, so we multiply by k here due to the chain rule. So now we have partial b partial t equals to this one, so we can just integrate both sides, so we will get b. And if we integrate this one with respect to t, integrating sign will become minus cosine. And also we need the chain rule, so we need to divide it by omega, because we need to integrate with respect to t, just like we integrate over t, integrate dt. Of course, we need to plus a constant, but yeah, you know there shouldn't be any constant there, so we can decide, or the constant should be 0. So yeah, so the integration for this term will be like k over omega em cosine omega t, because for the chain rule you need to divide minus omega, and then when you integrate it, you also have a minus sign. So two minus sign will cancel each other, so that the B field will look like this. And then we can also write the magnitude of the B field as Bm, so that we will have this relationship to be like this one is Bm, k over omega Em equals Bm, which means that Em over Bm is omega over k. And just now I already derived that omega over k is c, which means that Em over Bm is c, which is equation 33.4. So far we already explained why 33.1, 33.2, 33.4, also 33.3 is here. 33.3 is here due to the wave equation, the factor here. Okay, so yeah, so as long as we solve the wave equation in one dimension, so the solution will be ext bxt to be this one and this one, and which is what we have seen on the textbook, or on the original slides. If we really need the three-dimensional solution, we can actually write it as E of our vector. Our vector can be x, y, z, or in whatever coordinate you like, or we can just simply write it as a vector out in the space. So we in order to write it into 3 dimension, this term doesn't change because the time is still 1 dimension. This become 3 dimension. So the wave number becomes a vector. The wave number becomes a vector. This is also a vector. So these 2 vectors dot together to become a scalar, because this is a scalar without any dimension. So R is the wave propagating direction. R is the propagating direction. Okay, it will be like that. But yesterday I already showed you a YouTube, which is actually you can just check. You can just go to YouTube to search for polarization of light. Polarization of light, and then you can see one of the result will be called the Bell's theorem, and then you can find the video I showed yesterday. Okay, so in the textbook it also shows that ERMS is EM over square root of 2 BM equals BRMS is BM over square root. This is nothing special because it is a sinusoidal. We are used to use the root mean square value to specify the energy, something like that. So, and if you still remember, for the E field, this is the energy stored in E field or B field within unit volume. Within unit volume. Yeah, this is the energy per unit volume. Per unit volume. Per unit volume. So if you still remember, the equation is like the energy stored in the E field is 1/2 epsilon naught E square. E square. E is the magnitude. E is the magnitude. So in this case, it should be referred to EM rather than ERMS. So we have E square here. And if you still remember, I already mentioned that the equation corresponds to E field. When we change it to B field, we should just change E into B and then epsilon naught to 1 over mu naught rather than just changing E naught to mu naught. So we have 1 over 2 mu naught here. 1 over 2 mu naught here. And then we have epsilon naught on the top and then mu naught at the bottom. And we have D squared here. So this is the energy stored in the B field per unit volume. Okay, so now for the EM wave. So here it refers to the EM wave. It refers to the EM wave. So UE is 1/2 epsilon naught E naught E square equals 1/2 E naught CB square, because we already know that this expression E over B is C. So we have E equals CB. So we can just change E to be CB here. Okay, so we can just just distribute this square to C and B. So we have C squared B squared. And we know that C is 1 over square root of mu naught epsilon naught. So C square is 1 over mu square epsilon square. C square is 1 over mu naught epsilon naught, which means that C square equals 1 over mu naught epsilon naught. So this term changed to here, and then epsilon naught and epsilon naught can be cancelled. So it turns out to be B square equals 2 mu naught for the EM wave, which means that this is actually the energy stored in the B field, UB. Okay, in this case, it means that for the EM wave, the energy stored in the E field is actually the same as the energy stored in the B field. That's why the E field and B field have some sort of relationship with this one, EM over BM, to be the constant C. In this case, the energy stored in them will be exactly the same. And this guarantee the EM wave can propagate. Can be propagated freely. Which here, it also means that the energy per volume is, because UE is energy per volume in the E field and UB is the energy per volume in the B field. So the total energy per volume is U equals UE plus UB, which is double of them, because these two terms are actually the same. So when you add them together, it is nothing but epsilon naught E squared. So this is the total energy per volume. And and referring to the Poynting vector, is the energy per time per area. And then, if you still remember, in the textbook, it is like S equals E cross D over mu naught. You don't know why we have this factor at that moment, but here it tells you that suppose you have this energy per volume, and then the Poynting vector is actually the energy per area per time. So it is like if you have energy per volume, so you need to multiply by the length, and then divide it by the time. So this is like if you have length cancel with the volume, it will be the area. It will be the cross-section area. This is the propagation length per unit time. So this is actually the speed. Which means that this is energy per volume. You need to multiply by the speed of light to convert this one into the amplitude of the Poynting vector, which is related by energy per time per unit area. Energy per time per unit area. You need to multiply this factor to convert this one into here. So S, the amplitude of the Poynting vector, is the speed of light multiplied by this epsilon naught. And then we have E squared. So for this term, you have E equals CB. So you just change one E to be CB. So this E square is CEB, because E is CB. So we multiply E on both sides. So we have E square equals CEB. So totally, E square is CEB. So this one is C square epsilon naught EB. So we have EB here, and then this one is actually this one, because we also know that C square is mu naught, 1 over mu naught epsilon naught, which means that if we just move this term here, we have C square epsilon naught to be 1 over mu naught. So we have 1 over mu naught here. We have mu naught at the bottom, which means that the magnitude of the Poynting vector is this one, which agree with this one. Of course, this is E cross B, but at the very beginning, you already know that the direction of the E field and B field are perpendicular to each other, which means that the cross, when they cross together, the amplitude is nothing but the amplitude of E multiplied by the amplitude of B. So this is the case. And this concludes this part. And in the final exam, I will talk about, I will consider to have a bonus about the derivation for the Maxwell equation, but not in the free space, which means that we need to consider rho and j, not zero, not zero vector. So not in free space. Okay, so in this case, we will need to keep this term and also keep this term, which means that here I will still give you this curl of curl identity, and you of course need to plug in it correctly to get the final answer. And here we have mu naught j here, because we will ignore the free space assumption. So we have this term here, and also we have this rho over epsilon naught here. So of course you need to plug in here, so that's for the first step you take the curl on both sides, so this one remain the same, and then you plug in this term here. So this is not zero anymore, this is rho over epsilon naught here, and this one will be minus mu zero times curl of j, something like this. Yeah, so and of course you can just rearrange the term to get the final answer. So this is not good enough for the wave equation without the free space assumption. Of course you need to add two terms here, of course maybe positive or negative. Yeah, so this is the first one, and the other one, here you also need to plus mu j here, mu naught j here, and then the other two are still the same. So as long as we take curl on both sides, we have another term like mu naught curl of j here, and this one is still zero, so we still have this term here, and of course we have another term here. So this will be the bonus question for the final exam. And I think that's all for this chapter.